Chapter 6, Section 5, the second method, multiplying by LCD. Well, the reason we have a couple methods, and we're going to see, and you're going to get comfortable with hopefully both of these methods, because there's a kind of a time and a place, a best strategy for certain types of problems. So don't learn one of these and say I'm always going to use that. It may not be the best strategy to get to the answer with the least amount of steps, which is basically going to give you the least amount of chances for error. So let's look at this method. To simplify a complex rational expression by multiplying by the LCD. Number one, first find the LCD of all the rational expressions within the complex deal. I'll kind of point to this one. Well, look at all this one. Where are all the fractions? Well, it's one big fraction, but also 1/2, 1/3/4, 5/6, and 3/8 are all the fractions. 2, right? Well, I can find the LCD for 2's, for halves, 4's, 6's, and 8's, and find the least common denominator that will fit all of these. And if that's an easy thing to do, this is by far the best strategy to do. And what we're going to do is that magical multiplication by 1 again, using that identity property that allows us to make fractions equal to 1. And we're going to do this in a special way. When we find that LCD of all these fractions, I'm going to multiply by that LCD over itself, or over LCD over LCD. In other words, if this is the same numerator denominator, this is equal to 1 again. And then we simplify. No fraction expression should remain in a complex rational expression. And then we factor and simplify if we can. So let's see how they do this one. Again, we have a complex fraction here, a rational expression. There are really 4 smaller fractional parts in the addition and the subtraction. Well, what I want to do is find the LCD for halves, 4s, 6, and 8s. And I can do that by prime factoring each one. 2 is prime, 4 is 2 times 2, 6 is 2 times 6, and 8 is 2 times 2 times 2. Well, the LCD is all the prime factors that are in here, and then you only represent overlaps once. So here I have a 2, a 2, and a 2, which is, so I got 2 times 2, and then I got a 3 here, and then I got another 2 that's not here. So I end up with 2 times 2 times 2 times 3, which is 24. Now they do this in fractional form. I wish they would show the prime factorization again, because that's pretty key. And it's the best method to keep finding these LCDs. So that's what they're telling us here. I get the LCD for all these fractions, which happens to be 24. Well, I can multiply by 24 over 24, and I don't change the value because that's equal to 1. So that's what they do. They take 24 times 24. So here you'd have numerator times numerator, so I'd take 24 times this quantity right here, and we end up with a new expression. So they're showing this multiplication here again, and I end up with that distributing, and I end up with basically what I'm doing is all the fractional parts of my complex rational expression go away. This equals, which is an odd way, I'm surprised they don't show this. Anytime you multiply 1/2 times 24, this is 2 times 12. 1/2 times 2 is 1, you get 12. I'm really surprised at this point in a book they would show that any other way, right? And hopefully you're practicing that and you're not relying on your calculator, because that's good to really, that practice of even doing that multiplication that way is helping you when you get into variables. But what they find out, you get 24 over 2, which is an odd way to do it, but that's 12. When I look at this, I know that's 2 times 12, that's 12. Half of that, 2 is 1. Here I would go, well, force, here I got 24 is really 6 times 4, right? Well, I'd end up with 3 times 6 because the 4's would cancel out and I get 18. Here, 24 is 6 times 4, right? You end up with 5 times 4 is 20. Here, you have 3 times 8, so 8's cancel. I get 3 times 3 is 9. And I think if you start thinking that way, you're really going to do better in your future algebra courses. So we end up with this simple addition over a simple subtraction of integers. So, and I end up with 30 over 11. Make sure there's no common factors. Well, 11's prime, so that's in simplest form. So that's our method. Basically, I call this clearing these fractions here. So I'm going to convert basically all these fractions of 5 over 2a, 1 over a, 1 over 4a, and 5 over 6. I'm going to get rid of the fractional parts by finding the LCD of all 4 fractions in this case and doing that. Now, this one I would say definitely in my mind, as far as strategies, I would probably just do the addition. I'd go back to that first method we talked about in this case. This one I definitely would use this method though, because it's very easy to see the LCD between, now I'm only dealing with 1 over x and 1 over x squared and stuff. But we're going to show the method on both. So they find the LCD, and the first one is 12a. So I multiply the numerator and denominator by 12a because that's equal to 1. And again, they show this. Finally, they say, well, look at these things prime factored. Rather than saying this is 60a, they go, really, this is 5 times 2 times 6 times a. So they prime factor these things, and I wish they would have done the same thing with 12, just to be safe. And you start seeing that we end up with the fractions going away. Now in this case we end up with 30 plus 12, which is 42, and then I get 3 minus 10a, which I can't simplify. So I've cleared all the fractions, then I deal with this fraction, then check to make sure it's in simplest form. Like I said, now I might just add these and say 5a over 2a, 5 over 2a, and then this would be 2 over 2a, which I'd get 7 over 2a. I can add these pretty easily with common denominators. Basically add the fractions, then treat it as a division is the first method to review again. But this works. This always works. Both methods always work. This case, like I said, this is definitely the best strategy. I'm looking at this and I'm saying, hey, the common or the LCD between the x and x squared is x squared. So I multiply by x squared over x squared, and I end up with x squared minus x over x squared minus 1. Then I factor if I can, which you can on both of these, and I end up with a common factor of x times the binomial x minus 1. This is difference of squares, so we got a binomial again. I have no common factors. What can I do with binomials? I can look for difference of squares, sum and differences of cubes. This happens to be difference of squares, which is easy to factor. Hey, I got a common factor of x minus 1 over this denominator 1 of x minus 1. So I get x over x plus 1. This is definitely, when I look at this one, and then if you want to try it again, here's another one, but this is definitely the best method for these things. So I look, really what am I saying here is I look for opportunities to find an LCD quickly and easily, which usually means that clearing the fractions in this way, the smaller fractions in the addition or subtraction, is probably the best strategy.